Hello, everybody. Welcome to this live webinar today, a very special program on climate change. I am Kathy Grice, Senior Program Director at IEEE Future Directions. For logistics, we encourage you strongly to post any of your questions or comments to the panelists via the Q&A symbol that is located at the bottom of your Zoom screen. Post any technical issues, questions via the chat. This webinar will be recorded and made available at a later time. I will now turn it over to Rikambara. Thank you.
Rikambara, welcome you all in the webinar series of climate change program. So with this, I request Chair of IEEE TAB Climate Change, Dr. Wei John Lee, to kindly introduce about the TAB Climate Change program.
And welcome to this webinar series. I'm very grateful that with the help of the IEEE TAB FDC, we co-host this webinar series. And I'm Wei Jian Li. I'm currently the chair of the IEEE Technical Activity Climate Change Programs. And we have an excellent staff support, Randy, Angelo, and Patrick. And for this climate change program, the goal is try to create a platform for collaboration because the climate change is a very complex issue. And for this webinar series, we are focusing on developing new technology and tools, and this dissemination information and providing education contents, and also for the workforce development. So on this one here, that this year, our strategic goal is try to launch a climate change technical committee. And so at here, you can click the link to join as a membership of this technical committee. And then we also like to engage the discussion. We create a collaborative communities. And then also with the FDC, we also establish a new initiative on the climate change technology sustainability. This is working with the Planet Positive 2030s. Then we also try to have a collaboration with MSD contents team to provide the IEEE wide website. Because on this one here, this is all the information that we try to put it together and to support the technical activity on the climate change part. And then we also, on the expose and aggregation part, we complete the audit inventory of climate change effort across IEEE because every society, we are aware of the importance of the climate change. And a lot of society and the council, they have their own activity within the area of their expertise. So on this TAB climate change program, we try to bring everybody together and provide a common platform for everybody to work together. So, and then we also try to have disseminate the information of climate change contents to the large audience, like this webinar series. And we provide a conference, resource center, data port, and then webinar series. And then we try to promote the virtual event for the TA unit to larger climate change audience. So this is the effort IEEE put together, and then we try to collect everybody's, create a synergy on this effort. And that is my brief presentation here. And again, welcome everybody. And this is our first webinar series. And we welcome the presenter that I'll turn it back to the moderator. Thank you very much.
I would like to welcome all the participants to the first webinar of the Save the Humanity, Sustain the Climate webinar series hosted by IEEE TAB Climate Change Program Education Subcommittee. Under the TAB Climate Change Program, there are 4 subcommittees. Education Subcommittee is one of them. I'm Ramalata Marimuthu, leading the Education Subcommittee. as one of the activities of the education subcommittee, we are bringing this webinar series to tackle one of the biggest challenges facing our planet, the climate change. Our mission is to empower the individuals and the communities around the world to take action towards a more sustainable future. This cannot be the problem of a single government or a single non-government agency. Every one of the individuals have to take responsibility for the climate change, climate action, is also the responsibility of the individuals. So that is the reason we thought the education subcommittee's major goal is to bring awareness about the climate change and how to mitigate this climate change using what means, how everybody can collaborate, and what are all the important things that need to be educated to the younger generation about the climate change. So the whole aim of this education subcommittee and this webinar series is to throw light on what are all the worst practices that have been going on in this planet and how that can be reduced and how to bring in the best practices. So I would like to welcome you all again to this, and I hope that at the end of the webinar series, we all will be more knowledgeable about the best practices that we need to do individually. Thank you so much, Ritambara, for inviting me. Thank you.
Webinar series is Dr. Kalai Ramea. She is from Palo, Alto Research Center, and she will going to be speak on how can AI help on climate change action. Dr. Kalai Ramea is an interdisciplinary scientist who is working in the intersection of artificial intelligence and science. Currently, she leads a research area at the Palo Alto Research Center. Her research aims to leverage cutting-edge AI algorithms to tackle problem for social good, especially focusing on climate action in energy system. Her latest achievements was leading a $1 million DEPRA awarded project in collaboration with researchers from Canada and Germany. The project focused on developing hybrid AI approach for climate tipping points and intervention. Dr. Ramea received her PhD from University of California after obtaining her master's from University of Southern California. She completed her bachelor in engineering at the College of Engineering, Anna University. She has published over 40 papers in peer-reviewed journal and conference. Dr. Kalai Ramea is going to speak on how can AI help on climate action. With this note, may I request Dr. Kalai Ramea to kindly go with the session.
Thank you, Ritambara, and thank you, Dr. Ramlata Marimuthu, for giving me this opportunity. Can you stop sharing, Ritambara, so I can start sharing my screen? Thank you so much. Yeah, thanks all for coming today. Today we'll be talking about AI for climate action. And as Ritambara introduced me, I'll go over a bit about where I'm coming from, so you know my background in the context of what I'm going to talk about today. So I finished my civil engineering at the College of Engineering, Anna University, Chennai. So that's where I learned a lot about environmental systems, and that's where I got the passion about earth systems and things like that, and how my journey on climate change started. And after that, I joined University of Southern California to do my master's in systems engineering. Again, it's a system level engineering to understand the environment and such. So that's, it's a continuation of those. After that, I worked as a consultant for 4 years as an engineering consultant, where I worked with different cities and governments in California to better represent their infrastructure. And climate, again, was a huge part of it, but it was not as serious as we're talking about these days. So due to all this interest in the last several years, so I decided to go back to school for getting my PhD in energy systems modeling. And climate was my first choice because I loved thinking about the planet, thinking about the infrastructure, thinking about the systems. So I wanted to put all of those together. So what my PhD entailed was developing these mathematical models for climate and energy systems. So after that, I joined Palo Alto Research Center. So I did a bit of machine learning and data science during my PhD. So I joined as an AI scientist. As some of you may know, Palo Alto Research Center, or used to be called Xerox PARC, was at the forefront of human-computer interaction. It was the first place where the GUI was invented, the Ethernet was invented. So there are a lot of great inventions happened. And within the last 5 years, PARC has been focusing on a lot of things about energy and climate. So when I joined, it was at the burgeoning of those things. And I ended up setting up my own lab to work on AI for climate action, AI for energy systems. And I oversaw about 10 to 20 engineers and scientists during my time there. I recently quit PARC, which was like a month ago, to start my own startup. It's called Planet. I'll talk about that in a little bit as well. It's a climate AI startup. And this novel area is burgeoning now. So I'll talk a bit about what are we doing specifically in commercializing some of these concepts that we actually worked in at PARC and so on. So today's overview. So I'll give a very brief introduction to the kind of AI and ML techniques that are going on right now. It's supposed to be a primer, so forgive me if you already know about these things. And then how can we tackle climate change using AI? I'm going to give a few examples and focus areas, as well as the one project that I led last year, funded by DARPA. It's on climate intervention. So we're developing a hybrid AI model to tackle that. And also some ethical and fairness considerations, because as any AI system, we are supposed to think about these as we start deploying them in real world. It may not be as personal as a demographic-based system, but still, climate change as a whole, it's going to affect different parts of the world. So we have to think about the ethical and fairness considerations whenever we think about AI in this context. And again, about Planet, a little bit of a chime in there. And what can we do as the next steps, right? So a little bit of the terminologies, we're going to be talking about AI, machine learning, and deep learning a lot. So AI it's like a very common term that's used for ability of any machine to imitate human intelligence. So that's what we generally describe everything as AI. And in the last few years or so, machine learning and deep learning has gained a lot of momentum. Machine learning means it's any algorithm to incorporate intelligence into machine by automatically learning from data. So when you have big data, when you have supervised or unsupervised, when you have labels or not, which I'll describe in a bit, machine learning has become this go-to tool recently. But I also want to mention that AI encompasses a lot more than machine learning. However, machine learning has become a big component in the last few years. Again, within the subset of machine learning, there is deep learning. So these are neural networks that were developed many years ago, but then got popularity very recently due to the availability of computing powers. So what has happened was, with the availability of big data and with the development of neural networks, we have gone to a new era where we are able to learn more patterns or nonlinear patterns and high dimensional patterns and things that we were not able to do before. So it's put together, it's data and compute together. That's how we started going into deep learning a lot. And now there's another paradigm, generative AI, which you've all been seeing. It's the ChatGPTs of the world, the deep fakes and all of those things. We are going at a much more faster pace at this point. So to give a very small primer on what machine learning is, because we'll be dealing with different parts of it and later on, they can be mainly classified into three. Most of the machine learning you see are typically into supervised or unsupervised, and I'll talk about reinforcement learning a bit. So supervised is when you have lots of data and you do have target variables. Say, for example, you have a set of images and you're classifying them between a cat and a dog. Someone has labeled them a cat and a dog. Then you start either classification or, if it's a numerical variable, it's a regression. So you kind of do that when someone has already labeled or you have already got the labeled data. Unsupervised is when you don't know what they are, right? I mean, you don't know what the categories are or what that is. So that's when you go for unsupervised and mainly used for clustering. And if you are dealing with high dimensional data, you go for dimensionality reduction and so on. So any kind of problem you see in real world, for the most part, falls into these two buckets. more into supervised learning bucket at this point. So whenever people talk about machine learning, they either talk about classification or regression, commonly used, right? I mean, that's very useful for climate change in applications when I'm going to talk about in the next. And then you have reinforcement learning, which is a slightly less used, I would say. So this is mainly, say, for example, if you want to teach an agent or a robot to navigate an environment. So you kind of give them a reward and a penalty. For example, if you're designing a robot to go through a maze, you have to give them a reward when they find a path, and then you have to assign a penalty when they hit a wall. That's all you need to do. And then you train the model over and over, and then the robot will navigate to the exit if that's what it's needed. All right. So why climate action now? I think we heard that from Dr. Wei and Dr. Ramalata in many things. So I just wanted to put this particular news that came out last month. The ocean temperatures, they reached record levels in the Earth. Like it put us in uncharted territories. And we have already been seeing extreme weather events, whether it's heat waves or like hurricanes or wildfires in California, where I'm from. This has been happening over and over, and we are actually seeing the record temperatures, like 1 in 100-year floods or 1 in 500-year hurricanes. We are seeing that more and more happen. So no one is doubting that. But what happened recently in the last month, which has put everyone at the alarming state, is the ocean temperatures are off the charts right now. So when you look at the average daily global sea surface temperature, for example, you can see the red line here. This is 2023. We have never reached this place before. Usually we are here, and then obviously it's been increasing, but this has put us in a new paradigm that we don't know what's going to happen. So the urgency here is here. That's what I'm trying to say by this. And this is a complex challenge. So it's not like, oh, let's cool the earth using this particular technology. No, it actually requires a lot of different things. And it may have a lot of unintended effects when we are doing it. So we need all hands on deck and all technologies on deck to actually achieve this happen. And that's why AI could be one of the solutions that we can do that. So here's where it can help. Okay, it can process vast amounts of information, right? As I mentioned, like the availability of compute, as well as the algorithms now. AI can process vast amounts of data from like satellites, like weather stations, sensors. And specifically, if you look at climate data, when I'm saying climate data, it's like climate science. These Earth system model data, they're huge. They're in the order of terabytes or petabytes. So AI is like perfect for handling those things. And it's a complex system, as I mentioned, because climate is not like a single entity. So when you tamper with one region, it has unintended consequences in other regions, which I'll talk about in a bit in a few examples. So you may think you are solving a localized problem, but you may have teleconnections somewhere. So it requires advanced solutions. So you need to think it as a system as a whole. So a little bit about complex systems. So it's like, it's not a single entity. Like when they come together, it becomes a different organism. So some examples are like swarm intelligence, like, ants, or like the fish schooling behavior. So climate is one such complex system. So we need to think about advanced solutions in that aspect. And as I mentioned, AI has made significant advances recently. So this is a time to take advantage of what we have learned in other domains to apply on climate. And we have access to high performance computing now better than ever. So this is the right time to think about those things. Now, I put these 4 areas to talk about climate action, but these are not the only ones. I mean, these are just supposed to be representative of what we can do with the AI, but please feel free to think beyond this box. And I'm going to give examples of each of those things as well. So mainly, I want to say the combination of AI and the data processing capabilities, all of this is going to make so many tackling of the problems better. It can support decision-making, it can support innovation, and it can transition to a low-carbon future utilizing all of these technologies or focus areas that I mentioned here. So I'm going to talk about computer vision, natural language processing, data-driven optimization, and as well as the physics-informed machine learning, which we worked on last year for the DARPA project. Now, for computer vision, like as I mentioned, AI can process vast amounts of data. And if you think of climate data, this is in the context of satellite data, like remote sensing, drones, or any kind of image data, right? So it's very useful for observing Earth in that aspect. And classification and segmentation are the most commonly used algorithms in this area. As I mentioned, these are just the commonly used, but you can always think beyond the box. The availability of new satellite data, like there are some very high resolution satellites, there are private satellites being launched all the time. The possibilities are endless. So I think right now in this particular area, people have more data than they realize. And the traditional algorithms that they are typically using in climate change, they're not able to handle that kind of data. So that's where NOAA, NASA, and many such organizations, they're asking for help from AI scientists to actually sieve the data and distill the information that they can get to see what they can do, apply in different areas. So these are some common areas. So I'll go through one by one. So forest monitoring, and this is very commonly used, and it's also a very growing field. Like there's so many startups and so many organizations looking at it. So mainly like you're looking at Earth systems, right? So you're looking at observational data from satellites. So what it can do is compare historical data as well as the real-time data. You can track which forests are being deforested, for example. And also if they are at risk, like say, like Amazon is at risk, for example, because of climate change, then you can actually perform this time series or like a time, change detection of historical and present and kind of do an early intervention. Say if you observe certain areas drying up sooner than you expect, then you can actually, the government can intervene and then they can help out. And also the land use changes. There are so many illegal land use changes that are happening in the forest, like forest logging, like that's not supposed to be logged. You can actually observe this from satellite data and then say like, hey, this area is supposed to be green and now it's being logged. So it's helpful in many, many ways. So either for providing valuable information to conservationists, like, conservation organizations that they want to do, like nonprofits, or for like even corporates, like, many companies are now investing in forests in terms of carbon credits. So for them, when they are putting that amount of money, like, millions of dollars into a forest because they're offsetting their carbons, they want to make sure the forests remain as forests and not become something else, right? I mean, and there are companies like Pachama, for example, they're looking at this and they're purely using remote sensing data and AI to just monitor how that's going to change. And then they will inform the companies, yes, this is a valuable investment and so on. And secondly, coral reef monitoring. And this is another a biodiversity crisis happening in Australia and all over the world. It's getting bleached, the corals, because of the increasing ocean temperatures, as we saw in the earlier slides. So the biodiversity scientists and the conservationists, they want to see early warning signs. For example, they will go and do the underwater pictures, for example. Once you start looking at these pictures, you can kind of design an algorithm to say like, okay, this is the texture, or this is the structure, or this is the color. It's supposed to be healthy. You can immediately say like when something is off from the normal threshold, okay, this needs an early intervention. And the intervention could be in many ways. Like I will talk about that in the later slides. So they can actually protect these biodiversity because this is very important for preserving the planet as a whole. And then especially in that biodiversity crisis, because fish depend on them and then everything else, marine life depends on that. So one of the fastest affected species are coral reefs. So people are very curious about that and people are very interested in saving them. And thirdly, air quality monitoring. And this is super useful for countries like India and China, where we are seeing an increasing amounts of pollution. Now, you may think this is like tangential to climate change, but the climate change can aggravate air quality in a way. So, like one of the ways that people can do air quality monitoring right now, or currently doing air quality monitoring right now, is combining satellite data with ground sensor data. So think of it as like some sort of a data assimilation algorithm. So you're looking at the satellites. So there are satellites that can now see NO2, NOx, and carbon monoxide levels and so on. And then you can combine that with the ground sensors. Say, for example, you have these air stations everywhere, and then you can kind of verify, and then you can also augment the capabilities of satellites. Now, this is useful in case of like wildfires, for example. So when California had wildfires 2 years ago, we saw a huge uptick in carbon monoxide. It's a very poisonous gas. So, something like a real-time detection of carbon monoxide would have really helped, like in informing people, like, okay, there's going to be this wildfire in this region, so please be careful if you're suffering from asthma or something like that, so people can stay indoors and so on. And similarly just for air pollution, right? I mean, that itself kills people every year. So just looking at the NOx and then like implementing systems like, say, for example, if you implemented a system where to curb pollution, this can be used to monitor year after year and see if that is actually taking place, if people are actually doing those things as necessary to achieve that. So, and then the most important or most widely used applications in computer vision is precision agriculture. There's so many use cases here, so I'm going to touch a few. So this is very interesting because people use all kinds of data for this. They use satellite data, they use sensor data, they even use like ground, like taken images. And farmers there are many companies that have been tackling this. Farmers have been using this for like crop monitoring, water management, or, even like finding crop diseases. Say if you take a picture and then you can say like what kind of fungal disease is this, and then it's able to inform farmers like even before it spreads widely. Or even like, you look at the yield even before you do it, like based on the historic yield images, like you can say like, okay, this is a yield that might happen. And so the main important thing is like, as climate changes, right, the once practiced agricultural regions where we think, okay, here we grow rice or paddy fields, that may change over time because now it's too hot or now it's too dry. So this is becoming a very hot topic in the ag tech world, where they suggest farmers, like you may have to move your farming practices elsewhere so that you don't lose a lot of money. Basically optimize resource. Like if you don't have water to continue that, you may have to inform farmers before things become too late. So there are like a whole bunch of entities working on this, including private sector and public sector, to actually inform the food related work. So food security is going to become a big concern due to climate change. So this is actually a very important dear topic of mine. All right. So the next topic, before that, I just see chat if there are any questions. Okay, I can share the PPT for the recording, Dr. Asha Joseph. Yeah. So the next is data-driven analytics, like a pure, simple data-driven. So I'm giving one example here, but you can think of anything. So along with data, along with compute, I mean, we are seeing an exploding use of sensors everywhere. That, you may have seen this term Internet of Things, which means it's going to connect, the sensors are going to be connected everywhere. Say in this example that I'm showing here, smart grid is something that's becoming more popular. The factories may have sensors connected to grids, the smart houses may have sensors connected to grids, so they can actually optimize everything accordingly so you don't waste energy. So currently the decentralized grid, right? I mean, so what's happening is like people use their own things and then the companies use their own things. So ultimately you end up wasting a lot of energy. So when you do everything in synergy, like this is a complex system, as I mentioned earlier, like, they all work together, they all interact with each other. So that's where the data-driven analytics, so you can see like where the anomalies are, where the optimization might happen. Say, for example, you may have people buying more electric vehicles. You can observe the trend and then you can allot energy generation accordingly. So that way you don't people don't go out of power. So one of the things that has been happening, I'll give an example, even in the US that has happened is when we hit extreme weather. For example, this has happened in Texas over and over, whether it's a cold snap or a heat wave. immediately they go to brownouts or blackouts. Now, in the US, there's supposed to be like 24/7 electricity, right? So, but because of these extreme weather events, people are suffering a lot due to these blackout or brownout events. When I say blackout, it means like they just say, there's no power, deal with it. This happened last year when the cold snap happened. Austin was freezing and the pipes were frozen, and then people could not use electricity. So a lot of pipes burst in those places. These people are not used to handling the cold at that point because the cold was not supposed to happen there. Similarly, during the heat wave, the same things happened. Like they had a brownout saying like, oh, don't use washer dryer on these days. Or like don't use like electricity or keep temperature beyond like 70 degrees on these days and so on. So same thing has happened in California too. That's where the demand response actually helps. So a lot of the things like when we see extreme weather events, we need to have these grids adapt to those things. So more and more cities are thinking about these things. So we need to think the system as a whole, and that's where AI can help in terms of like data analytics and optimization. I'm going to check the questions one more time. Okay. All right. Okay, language. So this is an interesting area because typically, language has not been a huge part as part of climate action. The only place where I've seen natural language has been worked on is like the early warning systems deployed by the county or the city. Say, for example, if there is an emergency due to wildfire, then you can design a certain set of series of like evacuation messages. And AI could be used for that, like give like a GPS to escape a fire zone or something like that. However, with the recent advances in generative language models, there is a lot of potential. So one of the things that came out recently last month is this chat climate. So it's called chat IPCC. So IPCC is this intergovernmental panel for climate change. They release these reports every year on both climate science side of things as well as climate policy side of things. Now, these are like huge documents, like they are about like 100 to 200 pages long. And, basically scientists read them. Other than that, nobody else reads them. So someone made this app called Chat IPCC. So, you can go and like ask specific questions about your region, for example, and it should be able to say like, oh, this is the climate risk. So it's been super helpful to actually do like a Q&A on these things instead of just dumping 200-page document on someone. So I see there's a lot of potential here. So this is just one example, but you can think about so many examples as this is a new field, and there's going to be so many more ideas and use cases coming from language and climate. And finally, physics informed machine learning. So this is a project that we did earlier. And this is generally like a novel concept that has happened. So I will give a brief overview on what that is, and then I can talk about the specific project that we did. Now, take this as an example. So I start with this. Say an apple falls from a tree, right? So you can typically use like a gravity equation and then find out if this is the initial position of an apple, and this is the ground level, and this is the velocity, like where will it land with the wind and everything, right? So you can actually find that position. Now, you can also do it in a machine learning way. You can repeat this 10,000 times. Say, for example, you drop the same apple from the same position, drop it many, many, many times, and you can just fit a model like y equal to f of x. It's a machine learning model. It will learn adequately as long as it's this tree. You can do a data-driven model. Now, what if you have a new tree at this point? It's on a hill, for example. Now, this machine learning model may or may not work. So what's going to happen is, like, say, for example, you drop this from a different tree, it may even go upwards because it's on a hill. I mean, it may think like, oh, this is the final position. Because it learned from this tree, it may not generalize that well. This is what has been happening with a lot of dynamical systems that we have been looking, climate included. Think of any Navier-Stokes equation or any of those things. They have been training data-driven models purely. So when will this work better on this tree, on the one I'm showing on the right? When you train like 10,000 times here on the same thing, on the same apple, then it may work. But this is not feasible, right? If you want to generalize over all the apple trees, then this is not feasible. So that's where physics-informed machine learning comes. You instantly introduce gravity. Say the final position should always be lower than the initial position. This is one example, right? So it can be many other physical equations. Now this immediately generalizes to all the trees with falling apples, and we do not need many more data points as we require usually. Now, this is where physics-informed machine learning comes. So it could be as simple as introducing a constraint to a model. Or it could be as hard as like including like boundary conditions to the machine learning models. But this is a new area, and people have been dabbling with many dynamical systems such as climate in this. Now, for climate action, you may think, like I mentioned, it's a complex system with many, many teleconnections. So you tamper with one area here, it's going to have an effect on another area. So there are so many physics equations involved in this. So you have to be very careful when you're doing a pure data-driven model out of climate system. And also, here's another thing. Running each climate model takes weeks to months. So say, for example, you're trying to do a scenario, like you want to see what's going to happen when the world hits like 3 degrees, right? That's a scenario. And that can take weeks to months to run one climate model. Like when I say climate model, it's a very specific model called Earth system models that climate scientists run. It's a combination of several physical equations, and it takes like months to resolve it. Now, this is where machine learning is very helpful, but we also had to make sure that it's doing the physics correctly. People have been using this for like weather forecasting, for example, and they're incorporating physics in there. Say, for example, it can be as simple as like rainfall should not be negative. You cannot have a negative rainfall, like, it has to be at least 0. So simple things like that helps generalize the machine learning models better, or make generalizations faster instead of running these climate and weather models for a very long time. And I want to give a very brief example on our project called AI Beto. This is the one we use this for our developing our DARPA project. So before that, I have a one Q&A. So I'll just say, with AI and prevalence of ChatGPT, how can we trust this and about the implications of digital privacy? Very good question. Let me talk about ethics and fairness and privacy in the next few slides after I talk about AI Beto. Now, so this is a very interesting project. So firstly, I'll start with how do clouds impact climate, right? I mean, when you see clouds, there are 2 types of things. One are these fluffy clouds that you see. This is the one I'm going to talk about mainly. And the other are like breezy clouds that you see, wispy ones that affect climate in a different way. So mainly clouds are very impactful in terms of deciding surface temperature, precipitation, a monsoon, jets, and so many other things that we are looking at. Now that makes them ideal for certain things, including climate intervention. Now, when I say climate intervention, this is these are some experiments that are being thought of right now in many countries, where they are actually spraying sea spray, for example, salt water in the boundary layer cloud so that the reflection is better. Now, what that makes is, say for example, if I go to the California coast and I spray salt water there, the nuclei can divide, like the salt water can help divide the nuclei, and then the reflection is better. As a result, it cools locally. So people have been thinking about this because, we are, currently in the process of reaching some tipping points. Say, for example, if the ice sheet melts in Antarctica, that's a tipping point. So we go to a place where we cannot recover from it. So these are some strategies that can help avoid that. However, what will happen with deployment? And that is a question we need to consider. So if I disturb a region in California, will it affect somewhere in India? So things like that we need to understand better. So this is a project funded by DARPA as a result. So for example, if you disturb the coast of South America or coast of Northern Pacific, or even the Southern Atlantic, you can have different kinds of results. So there is a strong dependence on climate. So you cannot assume that you disturb in one area and then you can see like nothing happens elsewhere. So there are opposing effects. So for example, if you disturb this, you can have, Amazon rainfall might decrease here. And so that, necessitates like we need to run as many scenarios to know what's going to happen, right? And as I mentioned, like climate models take a month to or even several months to run one scenario. If you wanted to look at this area, like change cloud properties in this area and then look at what happened, then that's going to take several months. And again, this is another going to take several months. So people are not going to have time to actually test out every single combination of things. And government is interested in doing this, or want to know what are the unintended effects of doing this. So we have to look at these things. So let me show you the few things. So what we ended up doing was this machine learning model. So these are some cloud variables. So I'll share the slides later, but just make note that these affect the cloud reflective properties. So there are like the cloud amount, the cloud water, the radiative effect, and so on. And then the output variables, we are looking at how it changes in precipitation, how it changes in temperature or sea level pressure. So we did an architecture, something called spherical UNet. So it connects the input variables to output variables in a single spatial snapshot. So what that I mean by is, so I take the entire globe, we wrap it into a sphere, and then it maps to the input and output. And then that's how we learn the teleconnections in the Earth system. So instead of training one pixel to one pixel, we are training the globe as a whole. And this is a ground truth, like the data we trained on, and then the predictions that we got. And you can see that our model did a really good job in replicating the data. So what it learns is pretty much the snapshots of what happens, and then we time averaged everything, and then we are comparing the results. So now I'm not going to go into the detail. I'll show you the documentation page in a bit. So the workflow, mainly what you're doing it is not to replace the climate models, but to do some quick experiments. Like say, for example, if someone wants to see, okay, what happens if I brighten here? What happens if I brighten here? Then the model can quickly show, okay, these are some patterns. And then people can go run these climate models to show the more accurate results. This is really good for rapid prototyping, and that's where machine learning can help. It's used for people to run these different things so they can actually, the stakeholders can make decisions, policy decisions accordingly. All right. So this is the documentation page. So let me quickly show, this is the page. I'll share the link in this chat as well. So you can go there, you can see the descriptions of AI Vito, like what kind of training data that we did, and the physical constraints. I haven't talked about this, but you can go and see all the physical constraints that we used for this, as well as a little bit about like cloud brightening, what that is, what are some experiments that has been done right now. And as well as we have a visual analysis system that helps you do these prototyping. Now, all this code is open sourced, so you can actually go here, and there is a Jupyter notebook that you can click, and then you can actually see how to do this. So if you're interested in working with this data, you can just go and do this, and feel free to ask any questions that you have here when you're trying to work on this. Okay. So with that, let me come to ethics and fairness. So before, let me check a few questions. Can we use quantum computers to reduce time? Honestly, sure. I don't know. So quantum is very useful for certain things, right? Optimization, for example, the quantum annealing can be used for that. I personally explored quantum computing a little bit. I'm not sure if the architecture is there yet to increase the computing time yet. So it's out there. It's a live research topic. So feel free to dabble in it. I'm not sure if that's something that can be useful at this point, but definitely when quantum reaches that threshold to increase or optimize optimization speed, and can definitely be used for that. Is it justified to have new and complicated algorithms with so much of trial and errors, increased power of computers when you're talking about climate change? How are we reducing these effects? Very good question. So this thing, the climate models, they take a lot of compute too. So the high performance computing that's going to need, so we are going to do that trade-off, right? So the training of these models, like say, for example, we train these models on a GPU for like 2 days, and pretty much that's it. And then we are doing rapid prototyping after that. Now, as comparatively, if you're going to do in a different climate model, you have to run it for months, and you cannot even it's computationally intractable to reach all kinds of scenarios using climate models. And they also need high performance computing. So that's the trade-off we are here. We are not running this for mining Bitcoin. I mean, that's another thing altogether, but we're using this for a good cause. And honestly, like the computational wise, especially when you're training the GPUs, it's just like a 2 to 5 days. And after that, the inference is pretty quick. It's like 5 seconds. And so in that sense, it's okay. Same for weather forecasting. In that sense, it's okay. So if your training takes time, it's not going to take months and months. Language models take a long time. Comparatively, climate models are like very, very negligible. Will AI model be better for MPTT? I am not sure. I don't know about that area, so maybe someone else can answer that. Thank you. Okay, ethics, bias, fairness, transparency, all of that. So as I mentioned, we typically do not deal with personal or demographic data at a personal level. However, there's like a lot of ethical consideration in terms of regions. So the reason I picked this example, the AI video example, is for that, right? So when we were doing these marine cloud mining experiments, so what might happen is it's a power game. Some countries with power are going to do that, and some countries without power are going to be the receivers of that. So we need to be very, very careful in terms of designing something that's going to affect non-participants of that. So when we are writing the papers, when we are designing these deployments, we have to, we make a point to make it clear, like when you're perturbing something in a certain region, it's going to affect some regions that are in the global south countries. So this has been a consistent thing, and we make it a point to make the ethical considerations and fairness considerations of those things. And generally, when you think about all of this climate data or remote sensing data for that matter, the data availability is generally poor in global south countries. When I say that, I mean like the Africa, India, for example. And the model usually trained on the global north. I mean, they have private satellites, they get a lot of data. It cannot be directly transferred to global south. I've seen people doing that, train on agricultural fields here, transfer it, and then say, oh yeah, this is the yield you're going to get now. It's not at all the same. So you have to be very careful in considering the transfer of techniques when you're going from global north to global south. And you have to make sure that it is consistent with the indigenous practices there. So you cannot just go and technologically obsess people who are used to certain things. So there's an entire talk about how do you work with people when you're deploying something on the ground, especially in agricultural practices and so on. And also these climate models, right? For example, they are mostly coming from global north institutions. So there are hundreds of climate models when you talk about it. Each institution has their own climate models, and they all have different entry-level points, like initiation points. So they all can introduce their regional focus. They're not at many when you think about global south countries. So you have to be very careful about the biases that's going to introduce when you're doing that. It may be very favorable to one region that's of interest to them, but it may not be favorable to another region. So you have to be very careful in training these models as a pure data-driven model without consulting the experts. And very important, collaborate with domain experts. I come from the AI and the method side of things. We always had climate scientists in our team who can tell us this is a good thing or a bad thing, or this means this and this means that. So AI can solve things for sure. It's a hammer. However, it does not replace domain expertise and collaboration. So you have to verify every step of the way before going there. And that introduces transparency to the process, that introduces fairness to the process, especially in a topic like climate action. So you really have to talk about these things. So let me quickly check if they're continuing. All right, shall we harvest solar energy for electric vehicles? Do you mean like solar on electric vehicles or like, from the grid? Because I think from the grid, it's already happening. And there are companies that are tackling to channel the specific times of charging so that it comes from renewables. So there are work that's already been going there. So okay, with that, I'll go to Planet. So this is our new venture. So it's a company co-founded by me and Professor Singh, who is a climate scientist. So what we are doing is integrated climate and energy intelligence for the renewable energy sector. So when you think of renewable energy sector like solar, wind, and hydro, you have to know how much energy you're going to get every year. So the current practice right now is they look at historic trends and then say like, okay, we had wind like this, and this year, so this is what you're going to have. However, with climate change and extreme weather events, all of that is changing. And you may think that your wind farm is going to generate certain things in 1 year, but there are so many internal variabilities that's changing with climate. So you have to factor into that. Same with solar. You may think that your solar panel is going to be okay, but that particular year you may have a heat wave, which is actually bad for solar panels. So all of these things are, you have to make considerations, and the decision making has to be done accordingly. So we are doing that year-to-year climate variability and prediction, and as well as how to maximize your energy production and profitability. So you may have like policies changing in many markets due to climate change. So we want to incorporate all of that and give it to you and remove some regulatory hurdles. So this is our webpage, planet.ai. So if you go in there, you can actually see the kind of products that we are building and our focus areas. So renewable energy is our early market focus, but we are also looking at like insurance, real estate, and financial services. It's in a very early stage. So that's where we are right now. Super excited about working on this. So feel free to reach out about any questions that you may have here. So with that, I will end my talk. So this is my ID, kalai@planet.ai. So happy to take any questions now and as well as later. So thank you so much.
Hello. Yeah, thank you, ma'am. Thank you so much, ma'am, for sharing deep insights on how AI can help us in climate change, which is really, ma'am, it is really need of the hour to increase the energy efficiency, because nowadays we are harvesting energy which is based on different machine learning models to promote the adoption of renewable energy. It is really need of the hour, which in turn lower the carbon dioxide emissions while stimulating economic growth, which is essential for protecting us from the various hazards of the climate. So thank you so much, ma'am. Thank you so much.
Thank you. I see one more question that I forgot to answer. Is there any ML model which predicts changes in water table or underwater changes? Yeah, okay, that's going to be answered like, that's fine. Okay. So basically there are some sensor data that you can use, and also you can look at elevation and all of those things for underwater changes. Yeah, there's literature out there. Thanks. Is reinforcement learning helpful to measure climate change? It's a very broad question. So I'll say in one example where it might be useful. It's a kind of reinforcement learning. It's agent-based modeling. Basically in feedback loop, you can actually, say the grid optimization example that I gave, it can be helpful for, optimizing the grid. Whereas if you're asking to measure climate change, as in like a climate action, I don't think it's that helpful, because reinforcement learning is going to help you adapt to a certain environment. And the climate models do a pretty good job at that. And they are like a pretty good set of equations, physical equations. It's a very complex set of equations that have been developed over time. So they do a good job at that. And reinforcement learning might be a reductive process for it.
Ma'am, one more question is there. With AI and prevalence of ChatGPT, how can we trust this? And what about the implications of digital privacy?
So I mean, that's a very needed question, I guess. Like, people are thinking about all kinds of things on the trustworthiness of AI. So I touched and went on ChatGPT. I mean, like, climate change is not like a very, good topic for ChatGPT. Like, there's one application, but that's not like a very encompassing application. However, as we're going to see a lot of these trustworthiness issues with ChatGPT, and there are researchers focusing on how to detect disinformation. That's like a whole research topic in itself. For instance, when you query using ChatGPT, it sometimes gives like good answers. I mean, it's actually definitely helpful in designing certain things. And then it is sometimes hallucinating, right? It gives all kinds of disinformation. So there are researchers looking at techniques to actually identify hallucination versus actual information. For instance, if you query using ChatGPT many times, and you can look at the distribution of answers, and if it tends to be in one area, then it tends to be a good answer. Like, you might be right. But if it tends to vary across so many different things, say, for example, you ask for a paper citation, it just gives random things, then it is actually hallucinating. So there are techniques that people are developing to identify that. But it is an ongoing thing. It's a real concern. Like, disinformation and the trustworthiness of AI, it's a real concern. At least as well as climate change and the techniques that I discussed so far, they are tried and tested. So whether it's computer vision or physics and machine learning, they are kind of it's incorporating domain expertise into there. So you kind of build that robustness and the transparency into that process. So they are tried and tested. With respect to ChatGPT, I don't know. Maybe there are more techniques that's going to come that can be useful later on.
Okay, ma'am, thank you. One more question is from my side. Actually, ma'am, I am also working on AI-based solar energy harvesting, right? So I just want to know, because I worked for harvesting energy, whether it is solar or I can say body energy harvesting. But what for e-vehicle? Actually, smart grids are there. But if we go for on top roof solar panel, it is applicable or not?
I mean, yeah, there are algorithms that actually look at solar panels and then extract the amount of kilowatt or megawatt that you can get from that.
You also said that the pre-turbine observe.
Yeah. So there are algorithms that people have been working on that. You can use computer vision to actually detect the solar panels, as well as, like, depending on the weather, depending on the climate zone, you can actually estimate like how much solar you can get from a rooftop. So I think Google has a program on that. I can share the link later on. So there's like, it also includes the policies of the region and so on. So there are some companies doing that as well.
Okay, ma'am. Thank you.